In this video, we use the first translation theorem in the solution of an initial value problem, and it's just a first order differential equation. Notice that the right-hand side involves a t times an exponential times a sine of t, and we have y of 0 equals 0. Just as a reminder of what the first translation theorem says, it says that if you have e to the at times f of t, and you want to take the Laplace transform of that, all you have to do is take the Laplace transform of f of t. That's going to give you a function f of s. And then it's called the translation theorem because once you find that f of s, you're going to replace s with s minus a. So that's going to give us f of s minus a. So it's like the graph of f of s, just shifted a units to the right in the domain where we have s as our variable rather than t as our variable. So that's going to be appropriate for the right-hand side of this differential equation. Okay, so if I want to solve an IVP using the Laplace transform, I always start by letting people know what my notation means. So we're going to let the Laplace transform of y of t be big Y of s. And then we will take the Laplace transform of the differential equation and then substitute our initial condition into that result and simplify. Then we'll have an equation involving y of s. We'll solve for y of s, and then we'll take the inverse transform to get little y of t back. So let's start that process by letting the Laplace transform of y equal y of s, and then we'll take the Laplace transform of the differential equation. So we have the Laplace transform of y prime minus the Laplace transform of y equals the Laplace transform of t times e to the t times sine of t. Now, the Laplace transform of y prime is this. Since it's the first derivative, we start with an s to the first, and then we subtract an s to the 0 term. Now, s to the first is multiplied by the Laplace transform of y, and then we start at little y at 0 right there. So that's just the pattern for the Laplace transform of the nth derivative where n equals 1. We always have n plus 1 terms here. So if you're not sure if you've done this correctly, you can always count the number of terms. That usually helps serve as a check to make sure that you're doing this correctly. Since n is 1, I should have 2 terms, and I do have 2 terms. Then we subtract the Laplace transform of little y, which is big Y by definition. And then we have the Laplace transform of this guy over here, which is an example of the type of function where we would apply this. Here, our e to the at is e to the t. And then everything else is our f of t. So from this, we can see that a is equal to 1 because the coefficient of t is 1. And so what we're going to do is we're going to find the Laplace transform of t times sine of t in our table of Laplace transforms. That's going to give us f of s, and then we're going to replace s with s minus 1. Okay, so that's the plan. Let's go to our table of Laplace transforms now. Now, since we are taking the Laplace transform of a function, we are looking in the left column, and then the Laplace transform of the function of t is going to be in the right column. So we're looking for a t to the first times sine of t, and I think I see it. It's right there. It's number 22. That's the one. So according to this, the Laplace transform of t times sine of kt is 2 times k times s over s squared plus k squared quantity squared. So that's what I will apply here. And in our case, k is equal to 1. Okay, so it was 2 times k times s over s squared plus k squared quantity squared. In our case, k was equal to 1 because we had t times sine of 1t. And because we're using that first translation theorem, we're going to take this and we're going to replace the s with s minus 1. Now again, the reason that we're doing that is because there was an e to the at here multiplying that t times sine of t. So that means we take the Laplace transform of this piece and then we replace the s with s minus a. So this is giving us f of s, and then we replace the s with s minus 1 in our case. So we've got this. And that means the expression on the right-hand side is going to be 2 times s, but s is replaced by s minus 1. And then in the denominator, we have s minus 1 squared plus 1 quantity squared. And then on this side, we've got sy of s minus y of 0 minus y of s, and little y at 0 was given in our initial condition. That was equal to 0. So if we factor out the y of s over here, we have s minus 1 times y of s equals this expression on the right. So if I want to get y of s by itself, I'll just divide both sides by 1 over, or divide both sides by s minus 1, which is the same as multiplying by 1 over s minus 1, because dividing by 2 and multiplying by 1/2 are the same thing. So we have this expression here. Oh, looks a little bit blurry. Okay, so the s minus 1s reduce, and this s minus 1 will reduce with that s minus 1, and now we've got this right here. So I have 2 over s minus 1 squared plus 1 quantity squared. And that is the Laplace transform of the function that we're looking for. So all we did was we took the Laplace transform of the differential equation, and then we solved for y of s, which took a little bit. Now, in order to find the inverse transform of something that looks like this, I'm going to go to my table and see if there's anything in the table that matches this exactly. If there's not anything in the table that matches this exactly, I might look for something that has an s squared plus k squared quantity squared in the denominator, and take care of that s minus 1 by using that first translation theorem, but in reverse. So let's see what our options are by looking at that table first and trying to match this pattern. So now I'm taking the inverse transform. So I'm looking in the second column, I'm looking in the rightmost column, and I want a constant over s minus a squared plus k squared quantity squared. And I don't see anything like that here. And I'm looking in the right column on the left-hand side now. I don't see anything like that exactly. So now, since this exact pattern isn't here, I'm going to look for a constant over s squared plus k squared quantity squared. And that's actually, ooh, do we even have something like that here? Okay, actually, I think I see it. It's right here. It's number 25. I'm going to zoom in a little bit so you can see a little bit better. So it's number 25 right here. I've got this expression. Sorry, it's not quite even, but it says 2k cubed over s squared plus k squared quantity squared. Now, if we don't have the k cubed exactly, we can always multiply by a well-chosen one. So we can multiply by exactly what we need in the numerator as long as we compensate by dividing. The inverse transform associated with that is this function right here. So we'll have sine of kt minus kt times cosine of kt. That's the one I need, so I'm going to write that down on my paper, and then we will use that plus the first translation theorem to take this inverse transform. Okay, so we're here, and we've got this theorem, which kind of matches this pattern. Actually, I think it exactly matches that pattern with k equals 1, except that s has been replaced by s minus 1. So that tells me that when I take the inverse transform of this, I'm going to use my first translation theorem, but backwards. If I'm taking the inverse transform of a function of s minus a, and that's exactly what we're doing here. It turns out to be e to the at times the inverse transform of f of s. And the inverse transform of f of s is f of t. So I notice that s has been replaced by s minus 1 here. So that means if we have s minus 1 is equal to s minus a, that means that a must be 1. So when we take the inverse transform of that using this, so we're looking for y of t. Since a is equal to 1, this is going to be e to the 1t times the inverse transform of f of s. Now f of s looks just like this, but instead of an s minus 1 squared, it has an s squared in it. So we're going to have 2 over s squared plus 1 quantity squared. And that matches this pattern with k equals 1. So according to this is from the table. It says the Laplace transform of this is equal to this. That means the inverse transform, or the inverse Laplace transform of this, is equal to that. So I'm just pattern matching. According to this, we get sine of kt, where k equals 1, so it's sine of t, minus k times t, so that's going to be 1 times t, times cosine of kt. Since k is 1, we just get cosine of t. And that's our y of t. So we just combine those two to compute the inverse transform. And it's really that easy, guys. That is the function that you can take the derivative of and substitute into this differential equation over here. If you compute that derivative and you subtract the original function, you're going to get this. And if you evaluate that expression at t equals 0, you're going to get y equals 0. Let's check it out. T equals 0. I'd have sine of 0 minus 0. Yep, that's going to be 0. So cool. The second one is definite, or the initial condition is definitely satisfied. You could always differentiate and then subtract the function from itself to see if it satisfies the differential equation as well. I think it does. So remember, it's just a three-step process. You're just going to take the Laplace transform of the differential equation. You solve for y of s, which is the function, the Laplace transform of the function that you're looking for, and then you compute the inverse transform using the table and these theorems that we've just learned. So we've got our table, which lists lots of different options. We have a few Laplace transforms that we use so often that we commit them to memory. And then we've talked about the first and second translation theorem. So that is our example involving the first translation theorem. I'll see you in the next video to discuss an example using the second translation theorem.